Okay, so today we are going to do the last of the wire antennas, that is the log periodic dipole array. Or ND. Okay, the most striking feature of the log periodic antennas, any log periodic antennas, are they are broadband, or they have the largest possible bandwidth over which it can be used, at least compared to any other uh, dipole antennas. Okay, there are many log periodic antennas. We will do only one in this course, that is a log periodic dipole array. Okay, the log periodic dipole array, in some way it might look similar to an Yagi-Uda array, but there are some striking differences. The most important difference between log periodic and Yagi antennas are, in Yagi antennas we have seen that only one element was excited. We said that was the feeder element, and the other elements were not directly excited, and we said that they are the parasitic elements. You remember? In log periodic, however, all the elements are excited. Okay. In log periodic antennas, there are no parabolic, there are no parasitic elements. Okay. So, what is the basic structure of a log periodic dipole array? This is the feed. Okay. And now note the structure. See that the element size, it gradually increases as we move further into the antenna. Okay. And not just the element size, the element spacing as well. Okay. So, ideally, we say that now look the dimensions. This is Sn. Sn is the gap between the feeds. This is Sn plus 1. Okay. Dn is the diameter of the elements. This is Dn. This is Dn plus 1. Okay. If we connect all the elements by a straight line, okay, like this, then they intersect at a point. This angle we say is 2 alpha. This is Rn. And this is Rn plus 1. And what is Ln, as you might have guessed? This is Ln. This dimension is Ln plus 1. Then the most striking feature of a log periodic antenna is given by Ln plus 1 by Ln, that is same as Rn plus 1 by Rn, that is same as Sn plus 1 by Sn, that is same as Dn plus 1 by Dn, that is equal to 1 by tau, where okay. So ideally all these, they should increase in this ratio as the antenna moves on, okay. But practically we see only the ln and rns are increased like that. Sn and dn, they do not matter that much, but ideally for a proper log period antenna, all four of these ratios, they should vary in this manner. Is it okay? There is another parameter that is associated with the log periodic dipole array, and that is called the spacing factor given by sigma. Spacing factor given by sigma, sigma equal to Rn plus 1 minus Rn by 2 Ln plus 1. Okay. So keep these things in mind. So in practice, we are bothered more about these, and these. Even if they do not follow this, it doesn't matter too much. But L and R's, they are very important. They must be. The second striking feature is see how the elements are connected. Okay. Note that the two subsequent elements, they are connected 180-degree out of phase. Can you see that? The current fed to two subsequent elements, they are 180-degree out of phase. Is it clear from the diagram? The current fed by two subsequent elements, they are 180-degree out of phase. See how they are connected? That should be obvious from the connection. Is it okay? Is it okay? See how this connect. This is connected to this. This is connected to this. Okay. Once again, this is connected to this. This is connected to this. So this type of a zigzag or a crisscross connection, it ensures that the two subsequent elements, they are 180-degree out of phase. Is it okay? Now, can you guess this would be broadside or end fire, and if it is end fire, in what direction the beam would point? Do you want to have a guess whether this antenna would be broadside antenna or end fire antenna? Or if this is an end fire antenna, then in what direction the beam should point? The beam should point in this direction, towards the back or towards the front. It will be end fire, very good, because 180-degree and towards the front. Okay, we'll see about that. Any other guess? Also, can you guess why this antenna should be more broadband than the other antennas you have seen? Why this antenna is expected to be more broadband than any other antenna you have seen so far? Broadband means that it can be used. Uh, Remember that Yagi Uda specification we discussed in the last class, right? It was mentioned that the VSWR was less than 1.5 for a given frequency range. Remember the specifications we discussed in the last class? Okay. Here it means that the VSWR will be less than a value for a much wider range of bandwidth. Can you guess why? Can you guess why? Why this antenna is more broadband than the other antennas we have seen? Dipole antennas, folded dipole, loop, Yagi. These antennas we have discussed. So why this structure should be more broadband than any of those structures? What do you think? The answer is hidden here. The answer is question is hidden here because the length of subsequent antenna is okay. Look, this antenna is one. No subsequent. We are not using an array, so there are subsequent elements. Okay, the lengths are more. So how will the gain increase like that? And Ritika, the gain of this antenna is not that much. The Yagi antennas have higher gain. Okay, if you compare the gains of an Yagi antenna, log period antenna, Yagi antennas usually have higher gain. But this log periodic antenna, they have slightly less gain than Yagi, but they are much broader bandwidth. Okay. So we are not, for the moment we are not talking about gain, we are talking about the bandwidth. So why do you think this antenna should have a higher bandwidth than the other antennas we have discussed? Like to have a guess why? Look at the structure. Look at the structure. See, the lengths of the antenna's subsequent elements are different. Okay, this is shorter, this is longer, this is longer, this is longer, this is even longer. If I am drawing a small array, it could be more than 5, it could be 10 elements also. So it would be even longer. Okay, so if the antenna, the lengths are longer, different, then their resonant frequencies will also be different, right? If the lengths of the antenna elements are different, then the resonant frequency will also be different because what we have seen, the resonant frequency is slightly less than lambda by 2. Is it okay? The resonant frequency is slightly less than lambda by 2 that we have seen. Okay. So this will have the resonance at a much lower frequency. This will have the resonance at a slightly higher frequency. This will have a slightly more higher frequency, and this will have at the highest possible frequency. Oh, sorry, I made a mistake. This will have a higher frequency, this will have a slightly lower frequency, this will have a slightly lower frequency, and this will have at the lowest possible frequency. Obviously, because it is a function of wavelength, and wavelength is inversely proportional to the frequency. Right? So, for different frequencies, a different element would be at its resonant length and would radiate. Okay? So, that intuitively gives us an idea that why this should be a broadband antenna. Okay? Is it okay? Is it okay? Lisa, right? Any questions so far? Why this should be broadband? Okay. Now let us assume a mid-range frequency. Let me draw it. It might not be up to the scale, but you know that this is smaller. This is larger. This is larger. This is larger. This is even larger. This is larger. This is larger. Okay. Let us assume that the frequency is in mid range, so that this element, this is 1, 2, 3, 4, 5, 6, 7. Okay. Sorry. This is 7. Okay. So say that element 4, this is at the resonant length. Okay. The frequency is mid range. So what will elements 1, 2, and 3 be? They will be inductive or capacitive. Elements number 1, 2, and 3. They would be inductive or capacitive. Capacitive, very good. And 5, 6, 7 would be inductive. Right. Now, what is the phase difference of the currents fed to each element? Obviously, as we have discussed, the two subsequent elements, they are fed at 180 degree out of phase. Okay, as shown by the crisscross connection. Okay. So, what is the phase difference? The phase difference would be pi minus beta d, where d is this distance. Is it okay? The two subsequent elements, the phase difference would be pi minus beta d. Right. However, for the elements 1, the capacitive elements, this d is small. This d is quite small. Okay, because the capacity elements, they are very closely spaced to each other. D is quite small. Is it okay? So the phase difference delta phi is almost pi. Right? Since the capacitive elements 1 and 2 or 3, they are close to each other, d is very small. So phase difference is pi. Phase difference is pi. Okay. So see, these elements, they are very close to each other. Okay. And they are fed at 180 degree out of phase. Right. So their elements, their radiation will cancel each other. So the waves, the EM waves radiated by these two elements, they would be small and they would cancel each other. Right. So these capacitive elements, they do not have much contribution in the field. Is it okay? Right. So the capacitive elements, they do not contribute much to the field. Now let us consider the resonant element. Okay. Here the distance is almost lambda by 4. Okay. So what is the phase difference? Delta phi would be pi minus beta d. So pi minus 2 pi by lambda into lambda by 4. That is pi minus pi by 2. That is pi by 2. So these elements, they are 90 degree out of phase. Okay. So here a significant amount of radiation takes place, and that is towards the backward direction. Why backward? Uh, Actually, it depends on the exact frequencies. Okay, the most radiation takes place from the elements which are close to the resonant length. So depends on the frequency. If the frequency is slightly higher, then it will be from 3 4. It will be slightly lower, then it will be 4 5. Okay, both are possible. It depends on the frequency. The radiating element, it moves from 1 to 7 as the frequency decreases. Okay, so this radiate and gives the radiation in the backward direction, this direction. Okay, what about the other elements? 6 7, the inductive ones, what do they do? What do they do? First of all, they do not have much to radiate at all. Why backward? Because this phase shift. Okay, the phase shift is around pi by 2, so it will be along the backward. What about the sixth and seventh? Okay, first of all, they do not have much energy left to radiate because most of the energy that is already radiated by the resonant elements. Okay, so they have a very small amount of current flowing. I will show you the graphs, okay, of voltage and currents along this link later in this class. Second thing is that, see here, that this since this element is inductive, there is hardly any wave propagation in this region. Why? We will show it in the when we discuss the transmission line equivalent of this antenna. Okay, so they too do not contribute. So this is the very basics of the antenna. Now the transmission line equivalent of the antenna. This is my log periodic antenna. Okay, this part here there is no loading. This is equivalent to a normal unloaded transmission line. The equivalent circuit to this region is what we have seen for the transmission line. Okay, this area is called unloaded transmission line. This region, okay, the red region. The blue region, this is called loaded transmission line. Its equivalent circuit is like this. This is L, This is C. This is L. This is C. And this is CA. From where the CA is coming? From where the CA is coming? From where the CA is coming? Exactly. Because these lengths are lower than the rate, so it will be capacitive. Okay. So this is CA is coming from the capacitive nature of the lower elements. Okay, the shorter elements. This is called active region where it is getting radiated. So its equivalent would be L and C again from the transmission line and a ZA. Okay, and ZA, this is equivalent to the parallel of series capacitor, an inductor, and a resistor. Okay, so here the resistor effect dominates, and through this resistor, that can be this resistor that can be shown that is the reason why it is radiating, or you can say in the equivalent circuit the power is radiated through the resistor. Okay, this shows the radiation. And finally the fourth one, this is the reflective region. The L and C is always there. Here that is an inductor. Okay, reason is very clear. It's the higher elements there, the longer elements they are inductive. So these are the four regions of a log periodic antenna, right? Now you remember transmission line equations, the characteristic equation. It was something like this: d2v by dz square minus gamma square v, that is 0. Okay, we derived those things. What was gamma? Gamma was a propagation constant, r plus j omega l, g plus j omega c. In case of lossless, we assume lossless. For lossless lines, r equal to g equal to 0. So gamma equal to j omega square root of LC. Okay, gamma rather is beta equal to alpha plus j beta. So beta, the phase constant is this one. Okay, so beta equal to omega by LC. What will be the wave velocity? This is 2 pi by lambda. This is 2 pi f LC. 2 pi gets cancelled. So f lambda, that is v, that is square root of 1 more LC. Okay, remember we had this in the transmission line. Now see here, in the reflective region, we have a parallel combination of C and LA. Okay, in the reflective region, we have a parallel combination of C and LA. Okay, which could be inductive, which could be capacitive, right? A parallel combination of a capacitor and an inductor could be either inductive or capacitive depending on its value, right? What happens if it is inductive? What happens if it is inductive? So this becomes an inductive line like this, an inductive filter. If it is inductive, then it becomes an inductive filter. Okay, the wave velocity the beta becomes 0 and v phase becomes infinite, right? So there is no wave propagation. Okay, this is also a reason why. And if there is no wave propagation, all the elements would be in the same phase. So this is another reason why no significant radiation is taken place from the inductive zones. Is it okay? Okay, we'll continue after this in the second session. Time is almost over. Let me take your attention.